So the title of the project is Design of Microstrip Antenna for Early Kidney Stone Detection. So here we are using a microstrip antenna. So we are designing a microstrip antenna, a novel design, and which can be used for detecting kidney stone. So introduction. So in introduction, basically we are talking about the risk of kidney stones that is seen in human, like men as well as women, and also it is talking about the effect, the necessity for the kidney stone. That suppose if a person is suffering from severe pain when he has kidney stone, then for the diagnostic purpose the doctor, we will be seeing the hospitals, then that will be the advanced stage. Then there is no way to tolerate the pain. Even if we have taken the medicine, there are some time is required to come out of this situation. So there is always a necessity to detect the kidney stone in prior, and even though if we are going for any diagnostic purpose, people are using two main techniques to identify the stone. The first one is X-ray, and the second one is ultrasound scan. So both the technologies are nowadays using effectively, but these devices or these mechanism has its own disadvantages. For example, if you are using X-rays, the X-rays are using um, ionized radiations. Okay, so if we are, the human body is interfering with the, prone to these ionized radiations, so that will affect human body. So for more than 30 minutes, if you are in the X-rays, means the skin start having some issues like cancers and something. So X-ray is not X-ray is not always a trusted method. And if you goes to the next method called ultrasound, so ultrasound means the technique is using around 1 to 20 megahertz of sound waveform. But if you are using ultrasound, then sometimes very small small size of stone is not able to detect properly. And most of the case is that if you go for ultrasound, the scan images taken from the ultrasound, there is highly the people are highly dependent upon the doctor as well as the technical person who is there. Their skill is very much important to identify whether stone is there. So their experience and their skill is actually helping to identify whether the presence of tumor is there or not from the images. So that is one another, because human errors are there sometimes. If the skill and experience is not there, then to identify the stones from the images is quite difficult. So because of these existing disadvantages, we are proposing actually a new method that is called radar based, where here we are using a single antenna, and we are creating a kidney and a stone kind of structure, and the antenna will be radiating a signal towards the phantom, and from the phantom this reflected signal will be collected by the same antenna, and we will analyze it. Okay. So this is what the introduction part, and I have given few statics, like different age categories, what is the occurrence of kidney stone per 1 lakh of people, like the graph shows the count over there. And abstract is just we started our project work, so I'm giving a brief abstract, and the result and all is not included in the abstract. So we will modify this abstract later once we will give the report. So here we are proposing the same thing only in the abstract, like the severity of kidney stone that we face nowadays and the diagnostic difficulty. And we are proposing an antenna which is very low profile. That means the size of the antenna is very compact in size, and it is a simple structure, easy to fabricate, where we are using FR4, flame resistant 4 material, just like the PCB board. Such kind of material is used to design the antenna. and later it's a lightweight material also. So such a compact antenna is designed, a novel design with with these features. I'm designing the antenna, and later on a kidney phantom will be developed in the software called CST. So the antenna as well as the kidney phantom. Kidney phantom is nothing but we can't able to test the project in real time, so we need ethical clearance and all to test it in human beings. So we are creating the equivalent model in the software itself, just like a kidney properties like permittivity and conductivity, then density, then heat capacity. So these parameters of the kidney, the exact kidney will be taken, and those values are enter into the library, and we are creating the same kind of kidney phantom model, and we are simulating it in the CST software itself. So this was a project abstract, and the objective of the project is to design a compact, that is a small size, compact means small size microstrip antenna for kidney stone detection. That is the objective of this project. And I have mentioned a few purpose literature review, that in a sense some research already undergone in this particular area. So when I search through all the internet, I can able to find out only two papers till now published on this particular topic. The first one is over here, that investigation of kidney stone using microstrip patch antenna scanning system, which is published on 2015. And then later on we have one more paper in the same area, like which is published on 2020. So in these two papers, they actually designing, in the first paper ultrasound imaging is used to identify the abnormalities and to locate the stones in the kidneys. So they are using there, so to avoid, so they are proposing like ultrasound is affecting human body, which have some side effect to the human body. So to avoid this, they are actually going for microwave imaging. They are also using microstrip patch antennas, but in the design they are not using any CST kind of phantom. They are actually using a material. They are actually replicating the same human kidney structure using alternative material, not the actual kidney. Okay, so and in the second paper also they are using a monopole antenna. It's a new and design monopole antenna design is used, and they have used a frequency range of 11 gigahertz, and their antenna got a gain of 5 dB, and they are actually using for the testing purpose they are creating a kidney which consists of water and a small calcium stone. So instead of kidney, they are creating some artificial material, and they are testing the they are going for the identification of kidney stone using this setup only. Here also they are not using any actual, they are not testing it on human. Okay, so these are the two purposes we found out, and I had it latest 2018, 19 and 20 paper, and these papers are not actually talking about kidney stone, but the same kind of technology like microwave imaging technologies are applied to different applications like breast tumor detection, and in this paper we have new design, antenna designs are explained. So we can see that the different types of antennas used in these kind of applications, and what is the frequency range used for the antenna. So all these are taken from these literature surveys, and we inspired from these papers, and we have designed a new novel antenna. So now the block diagram is here. So we have kidney stone, a human kidney. Here I am mentioning the actual diagram of a kidney, but in the software we are designing a circular kind of model. So consider this will be the kidney model, and we are using a microstrip antenna. So a novel design, not this one. We are using I will see that antenna later, and we do the analysis, and then we will getting the reflected signal, that is called S11. Okay, that is how the flow of the project goes on. And here is the proposed design. So here we can see that this is a microstrip antenna, and this is the new design what we propose in this project. So we can see that a microstrip antenna always has three layers. So one will be the ground layer, and then the center will be the substrate. So the ground layer, you can see that here it is yellow colored. So actually it should be a full rectangle, but in the design I have made some modification on the back side, that is the ground layer. So you can see that only 1/3 of the ground is yellow color. So remaining 3/4 I have removed for getting the performance of the antenna. So that is, you can say here it has partial ground, not a full ground. Okay, then the green color material is called substrate. Here I am using the PCB board material, that is FR4, that is flame resistant material. Okay, then on top of this substrate I have placed a circular patch is the material who is going to radiate when I am applying a signal. So this is the patch, circular patch, and in the circular patch I have used alternate pentagon as well as circle in order to create some holes. We can see a green dot rectangular kind of holes are available in the different part of the patch. So this I have created like placing a cutting away a pentagon shape, then I am again pasting a circle inside that, like I keep on repeating so that I can able to create these kind of slots in this patch. Okay, and finally this long length is called feed, through which the signal is entering into the antenna and the antenna will be radiating. Okay, so this is the total structure of the proposed antenna. And now you can see that the artificial kidney phantom model with the stone that is created inside the CST design software. So both the antenna as well as this kidney phantom is designed inside this CST software itself, computer simulation tool. And here the outer layer is the kidney, and inside one you can saw a small circle that is considered as a stone. And the stone I have taken it as a crystal material, like a glass material, where because stone is formed by depositing calcium kind of minerals in the kidney. So I have considered it as a glass kind of material which having the same property. And the outer circle, that is the kidney, I can just consider as kidney. So here I have used the same properties of human kidney, like as I mentioned earlier, what is the property of the kidney for human being, like permittivity, conductivity, density, and heat capacity. So all those values I have given here, just like the actual kidney of a human body. And so now I'm going to talk about the different results of the designed proposed antennas. The first one is the VSWR. So VSWR in the sense voltage standing wave ratio. So for an antenna, if I am designing an antenna, for an antenna always the VSWR will be less than 2, and most of the cases it should be equal to 1. So for our case, our antenna is actually resonated at 4.2 gigahertz frequency exactly over here. So at that frequency range, that is 4.2, I'm getting the VSWR value exactly at 1. You can see that in the left y-axis, if the value is 1, the corresponding x-axis the value is 4.2. So we can say that at frequency 4.2 the VSWR value is exactly 1, that is equal to 1. So the designed antenna is a good one. Okay, so the VSWR is matching with the standard. Why I am telling 4.2 means I will show you the reflection. So we have this is the reflection coefficient. So you can see that the antenna is actually resonating. This tip over here, this is the resonation point. So this dip is actually exactly until 4.2. That's why we are taking that point over the VSWR. Okay, now other parameters of the antenna is, one is gain. So gain is nothing but output power divided by input power, that is the gain. So in this antenna, this is the 3D view of the gain plot, and we can see that at the resonant frequency f is equal to, that is frequency is equal to 4.2 gigahertz, we are getting a maximum gain of 1.477 dBi. Okay, so this is the maximum gain provided by this particular antenna. Since we are using a small size of antenna and we are using a partial ground, this antenna is not able to provide a greater gain. So because antenna always have trade-off, so that's why here the gain is 1.477. still we are getting a positive gain, so that is okay for the application. Okay, and the next antenna property, I mean parameter, is directivity of the antenna. Directivity is nothing but how the focus, I mean towards a particular point, how much energy is focused, that is called the directivity. The radiation is focused towards a particular direction, that is called directivity. So in this particular design, proposed antenna, at the frequency f is equal to 4.2 gigahertz, for the same resonant frequency we can able to achieve a directivity of 2.8, and that is also fine. We are getting a fine amount of directivity also. And now we talk about radiation pattern. Okay, so what is the radiation pattern of this antenna, proposed antenna? So the radiation pattern we will mention in two different side. One is H plane, the other one is E plane. So what is H plane means? H in a sense magnetic and E in a sense electric. So magnetic radiation pattern H plane, okay, and E is really electric. Okay, so so E plane radiation pattern and H plane radiation pattern. So when we consider H plane radiation pattern, we will keep phi value is equal to 90. Okay, so at phi is equal to 90 degree, then the radiation pattern is called H plane radiation pattern, and you can see this is the radiation pattern over a scale of 360 degree. Okay, and in this particular frequency f is equal to 4.2 gigahertz, we are getting the main lobe. This is a donut shape. The red color indicates a donut kind of shape, and the pattern is actually, main lobe of this particular radiation pattern is 160 degree. Okay, you can see it is pointing towards 160 degree. This blue line in a sense 164 degree. Okay, and when I show the E plane radiation pattern of the antenna, so the E plane radiation pattern of the antenna, we can see a figure frequency f is equal to 4.2 gigahertz, and the main lobe is actually exactly pointed towards 180 degree. Okay, so that is the radiation pattern of the proposed antenna. Now in order to find out the kidney stone using this method, so the setup is arranged in this manner. We will be keeping the antenna over here, and we will be placing the kidney with the stone phantom in front of the antenna. Okay, and we will start radiating the antenna, and the signal will be fall on the kidney. Then the signal will start penetrating itself, and it will touches the stone, and the reflected signal from this will be received by the same antenna, and we will go for the analysis. So this is how the mechanism works. So when the reflected signal is captured by the same antenna, we can able to plot this particular graph, that is called reflection coefficient, or we can say S11 graph. Okay, so here it is, this particular graph is against frequency in the x-axis and return loss, that is in the y-axis. Okay, so frequency versus return loss, that is the graph over here, and we are getting here I am comparing two graphs. One graph is like I am keeping only kidney without a stone. Okay, so that is the normal condition of a human being. So I am keeping kidney alone without a stone. I am radiating the antenna, I am getting the result back, reflection back. I will plot a graph that is highlighted in the blue color. Okay, green color. So you can see that green color, it is exactly over below the blue line. So you can see a green color over here, so which is having maximum depth in the resonation frequency. Now I am replacing that kidney, and I am placing the same structure of kidney, and I am keeping one stone inside the kidney. So that is the condition where kidney with the stone. Okay, so this time again the antenna start radiating, the reflection signal will be captured by the antenna itself. Okay, reflected signal, the same antenna will be capturing the reflected signal. Now I am plotting this graph. This time I am getting the graph which is like highlighted in the blue color. Okay, so we have two conditions. kidney with stone and kidney without stone. So in these two conditions, when we analyze the reflection coefficient, that is this particular graph, and we can see that I'm just highlighted this particular area which is in the circle, and I enlarge that portion. So in this area we can clearly see that the return loss value, the y value, okay, so the return loss value is lesser for a kidney with stone than a kidney without stone. So the green color graph is kidney without stone, and the blue color graph is kidney without stone, with stone. So kidney with stone will be having a lesser return loss value as compared to kidney without stone. So using this difference, we can able to identify whether this particular stone is present in a kidney or not. So this was our approach, and these are the reference purpose we used for the project. Thank you.